Hello, good morning. Welcome back to my channel, JBTeguihanon, Engineering and Chemistry Tutorial. Please subscribe. Let's jump into our topic today. Welcome to our study, refrigeration system. We are reviewing, and now we are going to review specific heat, right? Specific heat right here. We have this guy here, specific heat, right? So, what we now realize that different substance responds differently to heat. When 1 BTU of heat energy is added to 1 pound of water, it changes the temperature 1 degree Fahrenheit. This holds true only for the water. Other heated substances have different values. For instance, we note that adding 0.5 BTU of heat energy to either ice or steam cause a 1 degree rise, 1 degree Fahrenheit rise per pound, while in these states, ice and steam heated or increase their temperature at twice the rate of water. Adding 1 BTU would cause a rise of 2 degree Fahrenheit. Okay, this difference in heat, okay, rise is known as specific heat. So, very simplistic approach. Uh, and it is well understood, but in the engineering aspect, this is quite what we call it, difficult. So, if we go to the engineering approach, we go to the specific heats here. This is from thermodynamics for engineers, and this is my material PowerPoint presentation for that subject. So it's quite a bit difficult because you have to see to it that it's coming from the mathematical uh, manipulation, or shall I say derivation. So for a simple given system, only two independent variables are necessary to establish the state of the system, right? So if you try to graph this one, internal energy, you need to have at least temperature, and then you have at least specific volume to establish the value of U, right? So if you have temperatures at this point, this is suppose your temperature, this is your specific volume, you have a point here that defines your internal energy. So that this is mathematical presentation, this is graphical presentation. But in verbal presentation, we have had, we just had, you know, we had just finishing this in a simplistic way that specific heats for any materials is different. So far, what we have gone through is the water. 1 pound of water, if you add 1 BTU, it will raise its temperature from 1 degree. But it's just for the water only. Okay? So going back, we will derive from engineering point of view the specific heats. So using the chain rule from calculus, we express the differential term partial derivatives as du is equal to partial derivative of u over partial derivative of temperature. We held specific volume constant, then take the partial derivative of temperature. Plus, so these are partial derivatives of du over partial derivative of specific volume, taking T as constant multiplied by derivative of specific volume. Since u, small u is specific, stands for specific internal energy, that is specific weight, this is temperature, are all properties. The partial derivative is also a property that is called constant specific volume. Okay, and that is this guy here, partial derivative of internal energy over partial derivative of temperature. You hold specific volume constant, you have a specific volume or heat at constant volume. Okay, so that is how this being derived in the engineering. So the specific heat here is actually, there are two: specific heat at constant volume and specific heat at constant pressure. What I've just explained from engineering point of view is this one. Okay, so in a very simple way, everybody can understand this immediately. So by experiment, there are values here for specific heat. Okay, in figure 1.15, the specific heat table shows how much heat is required to raise the temperature of several different substances 1 degree Fahrenheit. So we have the specific heats, we have the substance. So this is why this is important, because we need to get the Q, the formula of Q. This is not heat transfer Q, but this is the degree, the content Q. Okay, the formula Q is equal to weight times specific heat times change of temperature or temperature difference. Okay, where Q is the quantity of heat added. Okay, yeah, that's it. That's the general formula of heat using the specific heat. Okay, in a very simplistic way, this is equal to wait, Yeah, in a very simplistic way, this is how it looks like. Yeah, here Q is equal to M times Cv times delta T. Okay, so this is specific volume he is using. Specific heat at constant volume, right? So that's the formula. I'm just showing you so that so what he's saying is that this Q is equal to weight, which is mass, times constant volume, specific heat at constant volume, times temperature difference. We sometimes write it this way. So this is the formula that you will be remembering. For a simplistic way, you have to look for this, okay, from the table, so that you will be able to continue your calculations. Suppose you are dealing with air conditioning. So what is the specific heat of your air? So you can see, right? So suppose you are dealing with beef. Okay, suppose you have 1 kg or 1 kilo of beets, and you want to calculate the heat. So you remember, heat is equal to mass times C sub V times delta T. So it doesn't matter whether it is capitalized or lowercase, right? So it's the unit is the same. It will not be changed because this is delta T, change of temperature. Okay, so you will look for this. You have 1 kilo, suppose. You have beets, which is Cv of beets, which is 0.9. Then suppose you have delta T, you can calculate the Q. Okay, this is how it is being used. Okay, the specific heat at constant volume. So that's all for now. Thank you for watching. Please subscribe to my channel, JBTeguihanon Engineering and Chemistry Tutorial. Bye for now. God bless.